We are back with the proof for Newton's method, or Newton-Raphson method. Let's quickly review the conditions of this theorem. So we would like to have a function from the reals into the reals. We'd like it to be infinitely many times differentiable, and we will assume that x0 is an initial guess. Then this iterative scheme applied infinitely many times should lead us to the root of, well, a root of the function. It doesn't have to lead you to the root. It only needs to drive you towards one of them. So let's take a look at why this works. We start by expanding the Taylor series around b is equal to x0. If we do this, we get the following. Recall that the Taylor series is given, Taylor series of f of x is an infinite polynomial. Well, I mean, it's a finite polynomial plus an error term. This is how it's given to us, but I like to say that it's an infinite polynomial because basically you can make n as large as you can. And then what's going on here is you have a polynomial, this polynomial centered at x0, well, it's usually centered at b, and its coefficients are always determined by its own derivatives, evaluated at the expansion point. And there's a small factor which you divide by to make sure that the series actually converges. I mean, that's not true. That's not why we divide by this constant, but it is true that the series converges with this constant and does not converge without it. Yes, exactly. That is correct. So we are here, enough with the technicalities, and I would like to write the first two terms of the Taylor series. Before I do that, let me substitute for b my value of x0. So this is the part which we are expanding around, basically. To get the first two terms, I'll basically plug in k is equal to 0 and k is equal to 1. I don't think that's outrageously difficult to follow. And here it is. So S0, 0, 0, 1, 1, 1. This is 0. My apologies. This is 1. This is 1. This is 1. And the 0th derivative of the function f is just the function itself. So I can simply write this as f of x0. And now I'm adding the following. f1 of x0 is the first derivative. And something to the power of 1 is just the thing itself. So this is what we have. And we would very much like, we want f of x be equal to 0. This is what we are hoping for. So we set f of x to be equal to 0. And the idea here is to say, or to ask, what is going to happen when I set f of x is equal to 0? Am I going to get some sort of information. So let's take a look into this. So I set this to be equal to 0. I'll write 0 here instead of f of x. And I'll get that on the right-hand side. Now I hope you don't mind if I take away f of x 0, and I also take away f prime of x 0, or maybe I'll actually add this. So let me add this. I'll add f prime of x 0 times x 0. Is this okay? I hope you're responding on the other side of the screen. I know I'm basically talking to myself right now. I think that's what too much of mathematics does to you. But but I hope you can feel me. I hope you can follow this proof in a good way. So after doing that, I will get f prime of x0 times x0 minus f of x0. That, on the other hand, will be equal to f prime of x0 times x plus the error term. Now, I hope you don't mind if I divide by f prime of x0, as long as it's not equal to 0, of course. This is an assumption we always have to make. Then here's what we get. So there's a series of implications, and I'm not writing it down, but so this would cancel out. And then this will be divided by f prime of x0. Then on the other side, we have this f prime of x0. It's going to get cancelled out. And then we're finally dividing the error term by f prime of x0. So that is good, because this looks exactly the same as our iterative scheme that we were hoping to get. What is this equal to, on the other hand? It gives us an x value plus some error term. What is this x value? It's the x value that makes f of x be equal to 0. Again. And so perhaps it is a good idea to use this coloring here to be more specific. Maybe a different color, maybe red. Red denotes it's daring. Whatever that is. So we are here, and x is the value that makes f of x be equal to 0. So in principle, x is the root. If you want to be if you want to get closer to the root, then this is what you do. You take this new x, and once you get this new x, you repeat the same process. So you set, well, not x, you set this to be equal to x1. So x1 is now closer to x. I do it again, and then I do it again, and again, and again, and again. And if I do it many times, then as n gets very large, the error term gets very small, because we're approximating the function more accurately using the Taylor series. And then this is actually equal to x. So at n, as n goes to infinity, en goes to 0. And this is what we get. So that is a proof. That is a proof. Put a big box there. And in a sense, if I take this x1 and I repeat the same process, I write x1 minus f of x1 divided by f prime of x1, then what happens is we get even closer to x. And if we do it enough many times again, then we will reach our value for x. And I think this is a very cool proof. It depends on the fact that the error term gets very small, and this we know from the Taylor series itself. We know that the error term, I don't want to say by definition, but by the theorem, it goes to 0 as n gets very large. Because the more accurate your approximation is, the lower the error is going to be. This is something that's been proven within the Taylor series, Taylor's theorem, basically, that we've utilized here. So we're utilizing this fact, and upon this fact, the proof works. If we don't have this fact, then this will not work. And it really shows you how powerful this statement is and how reliant it is on one single fact. Because if it's not there, then the proof fails, the proof falls. And I think that's how you should approach more general mathematical constructions. You need to ask yourself when they work, when do they not work, and why do they not work when they do not work. That is very important, and I think it gives you a whole different level of understanding that one could not obtain by simply solving the exercise and moving on. And this is all I have to say. So let us not diverge from the topic of this tutorial.